Imagine a nuclear power plant, but instead of a gigantic reactor complex covering hundreds of acres, imagine a much smaller reactor that can be manufactured in a factory, transporting to a site, and assembled like a massive industrial machine. It sounds futuristic, but engineers around the world are working on exactly this idea. They're called Small Modular Reactors, or SMRs, and they could change how nuclear power is built. But why would anyone want to make a nuclear reactor smaller? To understand that, we first need to understand how a traditional nuclear power plant works. Inside a nuclear reactor, fuel undergoes a process called nuclear fission. When atoms split, they release an enormous amount of heat. That heat is transferred to a coolant. The heat is then used to produce steam. The steam spins a turbine, and the turbine drives a generator that produces electricity. So at the end of the process, a nuclear power plant is still using a familiar engineering principle. Heat creates steam, steam turns a turbine, and the turbine produces electricity. The difference is where the heat comes from. Instead of burning coal or gas, nuclear reactors use energy released from atoms. Traditional nuclear plants can produce enormous amounts of electricity, but they also require enormous construction projects, huge buildings, large cooling systems, complex safety infrastructure, specialized equipment, and years of construction. That's where SMRs are trying to change the equation. An SMR is generally designed to produce much less power than a conventional large reactor, often around 300 megawatts or less per unit. IA.gov https://www.ia.gov/toddenergy/detail php d equals 67,584 and atom source equals chat.com. Instead of building one enormous reactor, engineers can potentially build several smaller reactor modules. And the word modular is extremely important. The idea is to standardize the design. Instead of treating every nuclear plant as a unique mega project, manufacturers could produce many of the same reactor components in factories. Imagine producing reactor modules under controlled factory conditions, then transporting them to the power plant and assembling them at the final location. This could potentially reduce some of the construction complexity associated with giant nuclear projects. It's similar to the way modern industries use standardized components to improve manufacturing efficiency, but nuclear reactors aren't ordinary machines. Every component has to meet extremely demanding safety requirements. The reactor must operate reliably under normal conditions, but engineers also have to design for situations where things go wrong. What happens if external electricity disappears? What happens if a cooling system fails? What happens if equipment stops working? What happens during an emergency? These questions are built into the design from the beginning. And this is where another interesting feature of some SMRs appears: passive safety. Instead of relying completely on powered pumps or immediate human intervention, some reactor designs use natural physical processes such as gravity and natural circulation to remove heat. For example, hot coolant can naturally rise while cooler coolant falls. Some systems can also use gravity-fed water for emergency cooling. The goal is simple: make the reactor safer by reducing the number of systems that must actively operate during an emergency. But SMRs aren't all the same. There are many different designs. Some use conventional water cooling. Others are being developed around gas, molten salts, or liquid metals. Each approach has different engineering advantages and challenges. So SMR isn't the name of one specific reactor. It's an entire category of smaller modular nuclear technologies, and their potential applications go beyond electricity generation. A huge nuclear power plant isn't practical for every region. Some electricity grids are simply too small to absorb such a large generator. A smaller reactor could potentially be more suitable for smaller grids. SMRs could also potentially supply power to industrial facilities, remote locations, desalination plants, district heating systems, and other energy-intensive operations. But now we reach the biggest reason SMRs are receiving attention. Electricity demand is changing. AI data centers are consuming huge amounts of electricity. Electric vehicles are increasing electricity demand. Factories are becoming more electrified, and modern cities continue to require more power. Renewable energy will play an important role in meeting this demand. But solar and wind power naturally fluctuate. Solar production falls when the sun goes down. Wind production changes with weather conditions. Nuclear power offers something different: continuous generation. A nuclear reactor can operate for long periods while producing steady electricity. That makes nuclear power particularly interesting for industries that need reliable energy around the clock. And SMRs could potentially provide that power without requiring the enormous scale of a traditional nuclear plant. But there is one major problem: cost. Making a reactor smaller doesn't automatically make it cheaper. In fact, the first SMRs could be extremely expensive. The whole economic idea depends on mass production. If manufacturers build one reactor, the cost can be very high, but if they eventually build dozens or hundreds of standardized units, they could learn from every production cycle. Manufacturing could become faster, supply chains could improve, construction could become more predictable, and the cost per reactor could potentially fall. This is one of the biggest promises behind modular nuclear technology, but reaching that point is difficult. The industry needs customers, factories need investment, regulators need to approve designs. Specialized components need to be manufactured, fuel supplies need to be available, and the entire system needs to prove that it can operate reliably. That's why the first generation of SMRs is so important. The first commercial projects aren't just power plants, they're also tests of whether the entire manufacturing model can actually work. And countries around the world are competing to develop this technology. The United Kingdom is moving forward with plans involving Rolls-Royce SMRs. Sweden has also moved toward deploying small modular reactors, and multiple advanced reactor programs are being developed in the United States and elsewhere. Euronews.com, https://www.euronews.com/business/2026/06/16/Rolls-Royce secures deal to build small nuclear reactors for Sweden. Atom source equals chat.com. But another issue cannot be ignored: nuclear fuel and waste. SMRs don't eliminate radioactive waste. Spent nuclear fuel still has to be handled and stored safely. Some advanced reactor designs may change how fuel is used or how waste is managed, but nuclear waste remains an important engineering and regulatory challenge. So are SMRs the perfect solution? No, they still face major challenges: cost, regulation, manufacturing, fuel supply, construction, waste management, and proving that mass production can actually reduce costs. But that's what makes the technology interesting. The real innovation isn't simply making a nuclear reactor smaller. It's trying to change the way nuclear power plants are designed and manufactured. For decades, nuclear plants have largely been treated as enormous construction projects. SMRs are trying to turn them into standardized industrial products, build the same design again and again, improve the manufacturing process, and deploy the reactors where they're needed. If that model succeeds, the future nuclear power plant could look very different. Instead of one gigantic reactor, there could be several smaller modules. Instead of constructing everything at one location, major components could be manufactured in factories instead of building enormous capacity all at once. Electricity generation could potentially be expanded as demand increases. And that could become extremely useful in a world that needs more reliable electricity. Electric vehicles, factories, cities, data centers, and advanced technologies all depend on enormous amounts of power. The question is whether SMRs can provide that power at a competitive cost while maintaining the extremely high safety standards required for nuclear energy. That answer isn't fully known yet, but the engineering race has already started. If manufacturers succeed in making small reactors safe, reliable, and economical at large scale, they could become an important part of the future energy system, not replacing solar, not replacing wind, and not necessarily replacing traditional nuclear plants, but becoming another tool for producing reliable electricity, because the future may not be powered by one single technology. It could be a combination of solar, wind, batteries, hydrogen, large nuclear plants, and thousands of smaller modular reactors. And that is why the tiny nuclear reactor could become one of the most interesting engineering technologies of the coming decades. The reactor may be small, but the engineering challenge behind it is enormous. If you enjoyed this engineering documentary, subscribe to the channel for more videos about advanced engineering, energy technology, machines, materials, and the infrastructure shaping our future. And I'll see you in the next video.